Hello and welcome to a third lesson, and we're going to call it Day 1 for Section 10.2. That's another lesson on vectors, and today we're going to introduce the idea of subtracting vectors, which is essentially adding a negative, as well as scalar multiplication. And the second idea we'll be looking at unit vectors. We're going to do this both graphically and algebraically. You've already seen what a vector looks like. Some terms like congruent and opposite. You've done some adding. You've found components. But we don't generally draw vectors in just open space. It's good to have some kind of reference for magnitude and direction. The coordinate axes allow us to break vectors into components and standard directions, basically a horizontal and a vertical. We used I and J for that. So if we want to make a drawing of vectors that are different in length than an original vector, we can look at something called a scalar, which is to multiply by a magnitude, and change a vector's length. So let's start with this vector A. It's pretty obvious what it is, but if we want to do 2A, we could see that by looking at this blue vector, it would look like a vector that's twice as long. And if we break it into its components, it's pretty straightforward from a graph. 1, 2, 3, 4, I plus 2j. Likewise, we can look at a vector negative 3a, this red one, and break into its components, which is going to be, there's negative 5, so negative 6i plus or minus, well, right? 2, 3, j. Okay, pretty basic idea. And what we've just seen, at least graphically, is how we can take a vector, we called it vector A, and change its length and also its direction. We made them larger, it's easier to multiply, but we could have also made the length shorter. This is an example of scalar multiplication. It doesn't change a direction other than to make it opposite. It basically focuses on the length of the vector, and we call that a magnitude. So if we wanted to look at, let's say, for instance, that 2a, the vector A, I believe, was 2i plus 1j. We could think of finding 2a by doing 2 times 2i plus 1j, just as a distributive property. And we would get 4i plus 2j. If you look at the previous slide, you notice that's exactly what we got graphically. Okay. So let's continue here. Give this a try, see what you get for vector B and its components, and then what negative B would look like. Okay. You've done this work already here before, yesterday in previous lesson. But there you go, negative 1i plus 3j. If we multiply by a negative, we would simply take this vector, negative 1i plus 3j, and multiply it by a negative 1. That gives us 1i minus 3j. Pretty straightforward stuff, probably. Let's get into more of what you saw yesterday with adding vectors. When you did this problem, you can obviously do it visually. You take the vector B, add it on the tail to the tip of A, and you get a vector visually that looks like this. That vector will be 1i plus 4j. Or we can do it by components, where a is 2i plus 1j, and b was negative 1i plus 3j. Simply add the components, you get 1i plus 4j. Okay. You're going to find the component. People who enjoy geometry maybe like the drawing. If you're more of an algebra person, the components works out nicely. All right. Seems kind of trivial, except now we're going to look at multiplying by a negative. That's the scalar, in this case negative 1. And this is how we're going to do subtraction. Not a huge step, but it's significant. So graphically, let's just go through this real quick. We would take this vector and move it in the opposite direction. It would be, in this case, my b vector is negative 1 plus 3. So negative b distributes to negative 1, and we get 1i minus 3j. We take that value and see that it's essentially what we would have drawn. 1 to the right, 3 down. And if we took that vector tip to tail with the a, we'd end up with a vector equal to 3i minus 2j. And let's see if we can get the same answer with components. The a was 2i plus 1j, and the negative b was 1i minus 3j. We add these two and we get 3i minus 2j. Sure enough, that's how we subtract. Not a huge step. Distribute a negative and we get subtraction. All right, so let's look at some work here. I'm going to ask you to try this on your own algebraically, see how you do, and then we'll come back and get these answers. Okay, 3a would simply be 3 times 5i plus 2j, which is going to equal 15i plus 6j. That is what 3a is. 2b is 2 times negative 3i plus 4j, negative 6i plus 8j. Okay, and now we'll try doing a subtraction problem. What we're going to do is take the previous answers, change a sign for one of them. Let's see what we get. Minus the vector negative 6i plus 8j. And this equals 15 minus negative 6. That gives me 21i. And then a 6. Whoops. Let's write these properly. That's a j. A 6 minus 8. 6 minus 8 is minus 2j. Okay. So first half the lesson here is to deal with scalar multiplication. That's what we see here. And then to subtract, we simply distribute a negative to the components, and that's called subtraction. Now let's take a look at how the magnitudes of vectors are dealt with. We do some operations later on that will involve some magnitudes. I just want to make it clear how magnitudes work here. If you looked at vector A, the magnitude is just like what you'd think from a Pythagorean triangle. It's simply going to be the square root of 5 squared plus 2 squared, which equals the square root of 29. Okay? And likewise, B is going to be the square root of negative 3 squared, which is a positive 9, plus 16. That's the square root of 25, which happens to be a perfect square. Now when we look at these two examples where we have the magnitude of individual vectors added together versus the magnitudes, the vectors added and then the magnitude, you're dealing with a slightly different order of operations. So let's take a look at this one on the left here. The magnitude of A, we just figured out, is square root of 29. I'll do a little neater here. Square root of 29. Magnitude of B is 5. So really, we just get 5 plus square root of 29. It's some decimal value. Don't like that. .385. When we look at the magnitude of the sum first, we actually have to go back and look at components. So the magnitude of vector A plus vector B, vector A is going to be 5 minus vector B's component for I is 3 plus 2 plus 4 is the J. And when we take that magnitude, we get magnitude of 2I plus 6J, which now is the square root of 2 squared, 4 plus 36, which is the square root of 40. We check that out, what that is. You see that they're not equal. And now if we want to take a look graphically at what this might be, we can notice that vector A, right, 5 up 2, looks something like this. B over here at negative 3 and up 4, something like this. If we did A plus B, we would get the vector that I show in the green here. Okay. And just looking at it, you can tell that the magnitude of A plus B, that's the green, won't equal the magnitude of A plus the magnitude of B. In fact, you could even say that you know which one will always be longer once we just take a quick look here. If I were to group these guys together and set them along this same path here, you'd see that the sum of the parts has to be greater than the magnitude of the addition first. So, in fact, to be more specific, you could even say that the value of the magnitude of the sum has to necessarily be less than the magnitude of individuals summed together. If you said they could be equal, what you're saying is you have a straight line.